Hello student, I am Dr. Ajay. Today I am going to discuss hybridization. This is a very important concept. Hybridization means, in a simple way, I want to brief it because it is a big these things terms where you have to understand many things. But I am telling you what is the common in all. Hybridization is a one chapter. You can tell it is a big. Then in this chapter, what is actually important things that I want to tell you only in the beginning. Hybridization means mixing of orbitals of the valence cell. In valence cell means outermost orbit. How many orbitals are there? Then these orbitals will mix and it will give new orbitals. The mixing of different orbitals, that is actually hybridization. Mixing of different orbitals having almost same energy. All orbitals will have almost same energy, and after mixing they will make orbitals of equivalent energy. Orbitals of equivalent energy in the same number. Suppose S orbital and P orbital is mixing. One S and one P. One S orbital, one P orbital is mixing. Then it will form sp orbital. Then their number was 2. One S, one P. Hence, it will form two we are mixing. It will form new 2 p orbitals. Two orbitals they will make. New orbital they will make, and its name will be sp. Just like two brother. Correct? Then sp like that. Sometimes 3 orbital will mix. One s orbital and 2 p orbital. Then it will make total 3 are mixing. Then they will mix and make new orbitals. That is called a hybrid orbital in the same number but of equivalent energy. Like that way, if one s orbital and 3 p orbital will mix, then they will make three orbitals, three new orbitals, and its name will be sp3, and all 3 new orbitals, that is called hybrid orbital, they will have equivalent energy. What is the purpose of hybridization or mixing of I can say orbitals? Then its purpose is that they should get equivalent energy, because S and P have different energy. S orbital, P orbitals have different energy. Px, Py, Pz, all are differing in their energy. Little difference, not much. S has different energy, Px has different energy, Py has different energy, Pz has different energy. But after mixing, they will make new orbitals in the same number. But now this time they will have equivalent energy. Then the process of mixing of different orbitals having different energy to give orbitals of equivalent energy. This is called hybridization. New orbitals will have the same number, that you can keep in mind. The simple example I am giving you, suppose you have 5 balls made up of sand, different color, maybe red, blue, green, like that way. 5 sand ball, SAND, sand ball you have. Then their color is different, 5 color. Then what you can do? You mix it, all 5, you break it and mix it. Again you make a new 5 you can say ball. Then now this time all color will be mixed in all. And 5 again you have made, it was 5 again you have made mix. That this time in all ball all color will be there. Then here color is indicating, you can say different energy was there. Now you have mixed. Then now all color is present in all, means now all 5 new 5 or white new 5 orbitals have now all color, means equivalent energy. This is the main things of hybridization. Okay. Now I am going in details. Okay. In order to explain the characteristics, geometrical shape of polyatomic molecules like methane, means CH4, NH3 and H2O, etc. Pauling scientist introduced the concept of hybridization. According to Pauling, the atomic orbital combine to form new set of equivalent orbitals known as hybrid orbitals. Unlike pure orbitals, pure means here what you have taken in the beginning. Beginning orbitals are called pure orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation. The phenomenon is known as hybridization. Which can be defined as the process of intermixing of orbitals of slightly different energy so as to redistribute their energy, resulting in the formation of new set of orbitals of equivalent energies and shape. Shape will be always also same like in the beginning. What original they were having, after mixing also they will have same type of shape. For example, when 1 2s and 3 2p orbitals, here you should understand only orbitals present in the valence shell, means outermost orbit. Only they will combine, not the, you can say earlier, like 1s, no. Suppose 1s, 2s, only 2 are there. Then only 2 orbitals belong to 2, only they will combine, not the earlier first. This you keep in mind. Only last orbit. Orbitals belong to last orbit, they will combine. Then I was telling you, for example, when 1 2s and 3 2p orbitals of carbon hybridize, then there is the formation of 4 new sp3 hybrid orbital, 2s1 and 2p3, px, py, pz, and 1 2s. Total 4 were mixing, and after mixing again they made 4 only, and name will be sp3, 4. sp3 hybrid orbitals. What is the actually main things, characteristics of hybridization? Means silent feature of hybridization. Question is asked in 1 marks and also in theoretical examination, subjective also it is asking. Silent feature of hybridization. Then the main feature of hybridization I am telling you. First feature, first characteristics, the number of hybrid orbital is equal to the number of atomic orbitals that get hybridized. Both will be equal. Second, the hybridized orbitals are always equivalent in energy and shape. Third, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Pure atomic orbitals also can make the bond, but they will be unstable. But this will be stable. When hybrid orbitals, they will make a bond will be stable. Now next point, that is the fourth point, these hybrid orbitals are directed in a space in some preferred direction to have minimum repulsion between electron pairs and thus a state of arrangement. Thus, again you listen, these hybrid orbitals are directed in a space in some preferred direction to have a minimum repulsion between electron pairs and thus a stable arrangement. Means in a space they will arrange in such a way that they should get less repulsion among the electron pair, because many electron pairs are there. Then they will arrange like that in such a way that repulsion will be less. Therefore, the type of hybridization indicates the geometry of the molecules. Means types of hybridization will tell about the geometry of the molecules. Now, what are the conditions? What are the conditions for hybridization? That also question is asked. What are the conditions for hybridization? Then 4 conditions are there. 4 conditions. Then first condition is that the orbitals present in the valence shell of the atom are hybridized. This is the important thing. Only the orbitals present in the valence shell of the atom are hybridized. This is the first condition. Second condition, the orbitals undergoing hybridization should have almost equal energy, not so much difference, almost equal energy. Third, promotion of electron is not essential condition prior to hybridization. Here promotion means that s orbital, suppose 2s and 2p orbitals are there, 2s and 3, these are there, 2p orbitals are there. As for example, listen, 1s square, 2s square, 2p2, like this situation is there, means carbon, 1s square, 2s square, 2p2, then last orbit is 2, then 4 electrons are there, 2 are in 2s and 2 are in 2p. Then here promotion means in excited state. In excited state means after getting the energy, After getting the energy, these 2s electron, which has 2 electron, they will go to the, you can say, third orbital of p, that is a pz. In p already 2 orbitals, 2 electron was there, then px py already was there. Then one was vacant, pz was vacant. Then 2s, from the 2s 1 orbital, it will go to the pz, means third one. Then now total 4. It became total 4 orbital, each have 1 orbital. Then this is called promotion. From the s they went to the pz orbital. Then now it became total 4, and s orbital 1 electron, and px py pz 1 electron. This is called promotion. Then that I am telling you as a fourth condition. It is not necessary that only half filled orbitals participate in hybridization. Not necessary. In some cases, even filled orbital of valence shell take part in hybridization. Not necessary that half filled only. If it is filled also, means two electrons are there in any orbital, that will also take part in hybridization. Okay, this is the fourth point. Third point, what I had told, again I am telling you, that was related to promotion. I have told promotion of electron is not essential condition prior to hybridization. It can take place after hybridization also. Then this I have told you 4 conditions of hybridization. First condition I told you, the orbitals present in the valence shell of the atoms are hybridized. Second, the orbitals undergoing the hybridization should have almost equal energy. Third, promotion of electron is not essential condition prior to hybridization. And fourth, it is not necessary that only half filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. This I have told the conditions. Now, just to come to the types of hybridization. Then there are different types of hybridization. Then here I am telling you, actually generally there are various types of hybridization involving s, p and d orbitals. The different types of hybridization are, I am telling you, first s and p. When s and p orbitals will take part in hybridization, then that time it is called sp hybridization. sp hybridization. And when 1s and 2p orbitals are taking part, then that time it is called sp2 hybridization. When 1s and 3p orbitals are taking part, that time it is called sp3 hybridization. Like that way, when s, p and d orbitals are taking part, then that time it is called sp3d. Tell you, if only one d is taking part, then sp3d. Then here you understand, when d is taking part, then d may be inner and outer. Means you have seen that D 3D 4S, 4S, 4P, 4D. Then you know that before going to before filling the 3D, electron is going 4S. That time it is called inner. Then that time that d orbital can take part in bond formation. Sometimes outer can also take part. Then two cases are there, inner and outer. N-1 for the 3D N-1. You keep in mind, two conditions are there, inner and outer. That's why it can make D this thing sp3d if one D is taking part. And again in that you can, if you can say D may be inner, then that time sp3d you are writing, that time you can write dsp3. D you write first, dsp3. D may be early, D may be later also, last also. Keep in mind. D may be early also, sp3, before the sp3, D will come, dsp3, or later also sp3d. Then if we can say 2D orbitals are taking part, then that time it will be called sp3d2. sp3d2 hybridization. And when like that way, I told you that sp3d2, then d2 sp3 also, d2 sp3 also. Then what I told here, different types of hybridization, that is sufficient to make almost all type of molecule. These orbitals will make finally bond with other atoms, and then molecule will be formed. These different orbitals will combine with other atom, like generally hydrogen, chlorine, fluorine, and they will make bond, and then molecule will be formed. Correct? Two parts are there. First they will hybridize, and after hybridization, when they have almost they have equivalent energy, then that time, after that, next step is formation of bond with other atoms. They should also be hybridized. If only one orbital is there, then there is no question of hybridization in case of hydrogen. Correct? They will not hybridized. Means only one orbital, the electrons are there, then that time there is no question. But same type of molecule will come, like two carbons are coming to combine. Then both, in all orbitals of both carbon 1, carbon 2, then orbitals belong to the both carbon, they should hybridize, and then only they will combine and molecule will be formed. Then this I have told you about the, you can say, different type of hybridization. Then now one by one I will discuss, because many molecules are formed then using this type of hybridization. Then I will start with, you can say, sp hybridization, because I told you many are there. Then all hybridization can't be finished in one day, and whatever is possible that I will discuss. Okay. Then sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals, sp, S and P mixed. Then after mixing they formed two hybrid orbital, that is called sp. Process is called sp hybridization. The suitable orbitals for sp hybridizations are S and Px. Generally Px, Py, Pz, anyone can mix in sp. S and P, any Px, Py, Pz is there, any one. Okay. The suitable orbitals for sp hybridizations are S and Pz. Okay, no problem, any can mix, either Pz or Px or Py, but suitable is Pz. If the hybrid orbitals are to lie along the z-axis, okay, then they will make spx, sp hybridization only, or exactly spx direction you have to consider. If px orbital is coming, that time spx. If y orbital is coming, py, then spy. If z is coming, then spz. But sp orbital will be there. Each sp orbitals has 50% s character and 50% p character. That is very, very important. Question is asked. Then because only two are there, S and P, then total 100%. Then 50% S character, 50% P character. Okay. Then each sp means sp hybrid orbitals. After hybridization, that sp hybrid orbitals has 50% S character and 50% P character. Such a molecule in which the central atom is sp hybridized and linked directly to the other central atoms possesses linear geometry. Linear means 180 degree. Correct? If now they have made the molecule, then it will be linear, like beryllium, BeCl, or beryllium, BeHH, or BeCl, linear structure, 180 degree. Okay. Or also you can say, here you can tell only yes, two are there, sp and sp, two orbitals are there, then two bond it can form. Then this will be linear, 180 degree. Then this type of hybridization is also known as diagonal hybridization. Okay. Now the two sp hybrids point in the opposite direction, not in the same direction. The two sp hybrids point in the opposite direction along the z-axis. Axis actually preferred is z-axis, but maybe with y also, z-x also. The two sp hybrids point in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes. Generally I told you positive only they will, positive lobes only they will overlap, and very small negligible negative lobes, which provide more effective overlapping. Positive means more overlapping, resulting in the formation of a stronger bond. Okay. Examples, I am telling you examples of sp hybridization. BeCl2 is the best example. Already I have told you now about the BeCl2, same things here. BeCl2. Then first you consider Be. beryllium. Beryllium 4 electrons are there. 4 electrons. 1 s square, 2 s square. Okay, 4. Beryllium has 4 electrons. The ground state electronic configuration of beryllium is 1 s square, 2 s square. In the excited state, one of the 2s electrons is promoted to vacant 2p orbitals, promoted to from s to p, vacant 2p orbitals to account for the bivalency, means 2s, it will 2 electron was there, then now 1 electron will go to the 2p, means 2pz or 2px, anything you can tell, no problem. Then in 2s only 1 electron is there and 2p 1 electron is there. Then now they formed s and p. sp, this is called sp hybridization, and now this 1s and 1p, they are mixing and they will make 2 orbitals, sp, okay, 2p orbitals to account for its bivalency, one 2s orbital and one 2p orbitals get hybridized to form 2 sp hybridized orbitals, 2 sp hybridized, sp 2. These 2 sp hybrid orbitals are oriented to opposite direction, forming an angle 180 degree. Each of the sp hybridized orbitals overlap with 2p orbitals of chlorine. Chlorine, know that in the last orbit they lack 1 electron, they have only 7. Then that is called 2p. These 7 electrons are in p only, 7th. 2p 5, correct? 1 they are lagging. That's why they want 1 electron. Then they will take part in hybridization. Then I am talking about that each of the sp hybridized orbital overlap. Now they are going to make a bond with chlorine. Then each of the sp hybridized orbital overlap with the 2p orbitals of chlorine axially, axis-wise, axially, and form 2 BeCl sigma bond. Axially, you know, sigma bond is formed by axis end-on overlapping, or axis-wise overlapping, or head-on overlapping. All have same meaning. Then they form bond axially. Sigma bond they form. sp orbitals of chlorine axially form the bond and form 2 BeCl sigma bond. Okay, diagram I will send you, I will give you. Already I have sent, in that also you can see. Again further if it require I will send. Okay, then BeCl2 I have beryllium chloride example I have given you, BeCl2. Now come to the sp2 hybridization. Here one thing I want to tell you, that before going to sp2 and sp3, here s and p, in s1 orbital and p3 orbitals are there, px, py, pz. Then in py3 orbitals are there. Then what will happen in hybridization? Out of 3, sometimes 2p orbital will take, means px and py only they will take part in hybridization. Third will not take part. pz will not take part. Means third one will not take part. Then that time suppose s and Px and Py is taking part. Then sp2, this is called sp2. Third one is not taking part. Despite sometimes it will have electron also, but it will not take part. In condition already I have discussed. Then that is called unpaired electron, unhybridized. That time it will be called unhybridized, when it will not take part in hybridization. And in sometimes all three will take part. All three will take part. Then that time it will be called sp3. sp3, and there will be no unhybridized. No unhybridized pure vital remaining, because all three taken part. Sometimes only one S and only one, you can say, already I have told, one S and one P, that is the sp, already I have told, sp. Two may not take part in bond formation, in hybridization. Then two are unhybridized. Even suppose they have one electron, suppose have one electron, all three have one electron, but in hybridization only one orbital of P. As for example, Px is only taking part, two are not taking part. Then they are called unhybridized orbital. Okay, this you keep in mind. Only in the beginning I have told you, because that is useful. You will understand later on. Okay, but now only here I have told you. It will be easy for you to understand. Now you come to the sp2 hybridization. Now you will understand fast. In this hybridization, there is a involvement of one S and two P orbitals in order to form three equivalent hybridized orbitals, one S and two P, total three. One S and two P, Px, Py, then total three. Hence, after the hybridization, you will get three orbitals, three hybrid orbitals, three equivalent sp2 hybridized orbital you will get. For example, boron trichloride BCl3, BCl3 boron trichloride molecules. Okay, that is the example. Here you can say the ground state electronic configuration of central boron atom. Boron will be in the center. The ground state electronic configuration of central boron atom is 1s square, 2s square, 2p1. 5 are there. Boron has 5 atomic number. Then 1s is no role, only outermost. 2s square, 2p1. 3 are there. Total 3 electrons are there. Then these 3 electrons means 2 electrons from the 2s and 1 electron from the 2p. In the excited state, one of the 2s electron is promoted to the vacant 2p orbital. Vacant 2p orbital. And as a result, boron has 3 unpaired electrons, 1 from S and 2 from P. As a result, boron has 3 unpaired electrons. These three orbitals, one 2s orbital and 2 2p orbitals, hybridized to form 3 sp2 hybrid orbitals, total 3 sp2. The 3 hybrid orbitals so formed are oriented in a trigonal planar arrangement. Purpose is the same. Why they are orientation? Then to make a distance, to reduce the repulsion. The 3 hybrid orbitals so formed are oriented in a trigonal planar arrangement and overlap with 2p orbitals of chlorine to form 3 BCl bond, that is the BCl3 bonds. Therefore, in BCl3 the geometry is trigonal planar with a Cl-BCl bond angle. Cl boron is in the middle. Cl-BCl bond angle is 120 degree. Okay, this I have told about the sp2 hybridization. Always orientation means in a space. Their purpose is to reduce the repulsion, and only in doing that way shape is changing. This is the main things I told you. That due to why they are doing orientation, going in a space, arranging in a different way, just to reduce the repulsion. From there, so many electrons will be, lone pair of electrons will be there, bond pair electrons will be there. Then to reduce the repulsion, they will make arrangement in different way. That is called orientation, just to reduce the repulsion. And in making, you can say arrangement, they are making different type of shape. That is the purpose of, I can say, that is the only for to explain all the things hybridization you are studying, shape of molecules. Now sp3 hybridization. Then here already I have told you, give an idea. This type of hybridization can be explained by taking the example of methane, CH4, methane molecule, in which there is mixing of one s orbital and 3p orbitals of the valence shell to form 4 sp3 hybrid orbitals, 1 from S, 3 from P. 4 sp3 hybrid orbitals of equivalent energies and shape. Shape also, what was the beginning? Here also same shape. There is 25% S character and 75% P character in each sp3 hybrid orbitals, because total are 100%. 4 orbitals are there, then equally share it, 25, 25, 25. Then only one S is there and 3p are there. That's why S character is becoming less, only 25. And 3p was there, then 75. Then S characteristic in all sp3 hybrid, I am talking about the hybrid, 4 are there, then S character is only in each 4, S character is 25%. 75% is P character. That's why if you see the shape, then S will show less, very less, and P will be big. And dumbbell will be there, P. Then after the mixing, they will make a new hybrid. That structure will be entirely different. Then in the end, it will come just like a very small lobe, and one will be big lobe. After these things, after mixing, means hybrid orbital I am talking about, S and P. Then due to the P, because 75% P character is there, then it will show big. One lobe will be big, other lobe will be very small, because that is due to the S character, 25%, and second lobe will be very small. Then if you will see the diagram, then you can understand why it is so small. Okay, then there is 25% S character and 75% P character in each sp3 hybrid orbitals. The 4 sp3 hybrid orbitals so formed are directed towards the 4 corners of the tetrahedron. Keep in mind, the angle between sp3 hybrid orbitals are 4 are there, no? Tetrahedron. Then what are the angles? The angle between sp3 hybrid orbitals is 109.5. In diagram you can see. Already I have sent also last video. In that also I will send, but anywhere you can see. The angle between sp3 hybrid orbitals is 109.5 degree. Okay. The structure of NH3 and H2O molecules can also be explained with the help of sp3 hybridization. In both cases, sp3 hybridizations are there. In NH3, first to understand, in NH3, the valence shell means outer electronic configuration of nitrogen in the ground state. Actually, 7 are there. Now, the 1s square, 2p5. Then you are talking about the 5. Then 2s square, 2p3. Then 2p3. Then 3 electrons are there, 1 in each, px, py, pz. Each have 1 electron. Okay, and s have 2 electron. Then now we can understand the valence shell electronic configuration of nitrogen in the ground state is 2s square, 2px1, 2px, 2py1, 2pz1, having 3 unpaired electrons in the sp3 hybrid orbitals. Here no promotion, 2s square is there, 2s square is there, but they have hybridized. No, s electron is not promoted, keep in mind, 2 electrons are there. Without promotion they have taken part in hybridization. What I have discussed in condition, here it is applying. Then all have, you can say, have taken part in hybridization. Then 3 unpaired electrons in the sp3 hybrid orbitals and a lone pair of electrons is present in the fourth one, total 4 orbitals. Then in fourth one, lone pair is there, means 2 electrons are there. Then total 4 hybrid orbitals are there. Then out of these 3 hybrid orbitals which have single electrons, these 3 hybrid orbitals overlap with 1s orbital of hydrogen atoms. 3 hydrogen atoms will come, 1s orbitals of hydrogen atoms to form 3 NH sigma bond, NH sigma bond. We know that the force of repulsion between a lone pair and a bond pair is more than the force of repulsion between 2 bond pair of electrons, BSEPR theory. According to that, then due to this force of repulsion, what will happen? The molecules thus gets distorted and the bond angle is reduced to 107 degree from 109.5 degree. This happens due to the repulsion. Apply the BSEPR theory. The geometry of such molecules will be pyramidal. Then ammonia has a pyramidal structure. Already I have given in the last video structure. Now come to the H2O. In case of H2O, the 4 oxygen orbital means now oxygen, you know, oxygen 6 electrons are there, 1s square, 2s square, 2p4, then last orbit 2s square, 2p4 you have to consider, total 6 electron. Then here what will happen? The 4 oxygen orbitals, 1 2s and 3 2p undergo sp3 hybridization, forming 4 sp3 hybrid orbitals. Then here you have to understand 2s electrons are not promoted. and 4 are there. In px, 4 electrons are there, then 1 each, and again px will have 2 electron. Means 2s also have 2 electron and 2p also have 2 electron, and y and z, they have single electron. That you have to keep in mind. But there total in hybridization they are taking part 2s and 3 2p orbitals undergo sp3 hybridization, forming 4 sp3 hybrid orbitals, out of which 2 contain 1 electron, and each this 2 electron, out of this 4, 2 contain 1 electron each, and the other 2 contain a pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry. This is also tetrahedral geometry, with 2 corners occupied by hydrogen atoms. Suppose hydrogen came, they made 2 bonds, they will make sigma bond, with 2 corners occupied by hydrogen atoms, while the other two by the lone pairs. Here you have to understand 2 lone pairs and 2 hydrogen bond, total 4. Then 2 lone pair have not taken part in bond formation. Only orbitals which have single electron, they have taken part, hence 2 lone pairs are remaining. That's why it is called that tetrahedral. But 2 lone pairs are there, including that it is called tetrahedral hydrogen atoms, while the while the other 2 by the lone pairs will be there. The bond angle in this case is reduced to 100.5 degree from 109.5 degree. Tetrahedral had bond angle 109.5, but due to this lone pair repulsion and lone pair bond pair repulsion and bond pair repulsion, VSEPR theory, following the VSEPR theory, that angle you can say which was in the 109.5 degree in tetrahedral, now in water it became water molecule 104.5 degree. Okay, and the molecules thus acquire a V-shaped or angular geometry. Okay, this structure also I have given in the last class video diagram. Okay, you can see. Then this I have discussed today. Today I am stopping only here. I have discussed about the hybridization sp, sp2, sp3. Now other hybridization little complicated, like these things. Methane you understood. Acetylene triple bond, and ethylene double bond. Means double bond or triple bond, how it is formed, that, and related to D, I will try to discuss in the next class. Thank you.